Yeah, hello. Thanks for the invitation to speak here. Great conference. I'm Sergio Boixo from Google Quantum AI, and I'm going to talk mostly about NISC scientific applications. The first thing I would like to do is actually, say thanks to the team at Google. We're 100 people and growing. We're hiring. You can go to that webpage and find open positions. And the work I'm going to be talking about is actually being done by the team, not by me. So we have a hardware roadmap, as other companies do. The long-term goal is to build a fault-tolerant quantum computer with around 1 million physical qubits, 10,000 logical qubits. And where we are now is at the stage of, we achieve our first beyond classical experiments, meaning our first well-defined computational task that you can perform in our experimental hardware now that are very hard or impossible to reproduce with the state-of-the-art supercomputers. So there is a long roadmap, right, that is going to take us to get there, to get to a fault-tolerant quantum computer. Not just because we have to scale from 50, 100 physical qubits to 1 million, which is itself hard, but also because we have to lower the fidelity. So why is this the current roadmap? Well, the reason is that it's very hard to scale fidelity in general. And although we keep improving fidelity in Transmons and other platforms, we're probably going to keep hitting fundamental limits. We keep changing the designs of the qubits. And it's very hard to make a very concrete roadmap that tells you, after this point, I just need to scale the number of qubits. I solve the fidelity problem. Or put another way, we learn from classical computation that digital computers scale much better than analog computers. So at some point, once we can do fault-tolerant quantum computation, once we can do quantum error correction, then we're truly doing digital quantum computation. We don't need to improve the fidelity anymore, right? We just need to do scaling up more of the same as we learn is the right path, at least for classical computers. So that's the long-term roadmap. So where are we on that roadmap? Well, we published this year a paper on the repetition code. The repetition code is, the quantum repetition code is the 1D version of the surface code. So in this paper, we saw that we can correct either bit flip or phase flip, but not both at the same time. To correct both at the same time, you need the 2-dimensional surface code. This is just the 1-dimensional surface code. But we see that even as we do many rounds, up to 50 rounds, the logical error rate indeed decreases exponentially with the distance of the code, either for bit flip or phase flip, both of them. And the exponential suppression was actually quite good. It's this factor that we call lambda. We need lambda to be bigger than 1 to be above threshold, meaning that as we increase the code distance, the logical error rate decreases exponentially, and we have a nice lambda. So all the components are working to really make the jump towards a scalable surface code error correction. But we do not have the fidelity yet when we publish this paper. So on the right, you can see what is the current error budget. So one nice thing about doing these kind of experiments is you can compare your models with your experiment, and you can budget where your errors are coming from. And on the plot of the left, you see 1 over lambda. So here, you want to be below 1 over lambda, to have error correction, exponential suppression of errors. And you see that for both the repetition code and the, for the repetition code and bit flip and phase flip, we actually understand quite well where the errors are coming from, meaning we have this component error model that we measure independently. So we measure independently what is the qubit gate fidelity, what is the T1 time, what is the measurement error. We put it all together in simulations, and it gives us an estimate of what lambda will be, what error correction performance we're going to get. And it matches quite well, even without crosstalk and leakage in this particular place. Crosstalk and leakage will actually become more important into the experiments, though. But at the time that we published this paper, as you can see on the last column, if we actually apply the same component error model to the surface code, then we're not below threshold yet, meaning we need to work improving the fidelities, which is what we've been doing. Something that is interesting, actually, once you actually start doing experiments, I'm working in more detail over models, is that a lot of the error is actually coming from just the idle time that your qubit is not doing anything, the data qubit is not doing anything, but you're measuring and resetting the ancilla qubit. So that's the blue bar, and you can see that the blue bar is even bigger than the red bar, which are errors coming from the 2 qubit gates. So that tells you that you really need to work on all the components and really do detailed simulations to understand where you're going. Okay, so that's the long-term roadmap. And I will say, quantum computing is exciting. I think I don't need to probably argue that for this audience because the field is progressing. We have a reasonably realistic long-term roadmap, and we know that there will be a big payoff. But nevertheless, and this has come up multiple times, like all technologies, probably quantum computing will go through, well, the standard Gartner expectation cycles, meaning we might be getting closer to the peak of inflated expectations, and eventually, we'll have to go through the sort of disillusionment, meaning, on the path to a fault-tolerant quantum computer, well, it's still a long roadmap. We want to have interesting applications to do in the meantime to really go through this valley, right? So we're actually keep doing interesting scientific work. So I will say in the next few years, when we get to the fault-tolerant quantum computer, we are indeed going to be able to see interesting scientific applications. And arguably, we're seeing this already, but not everywhere. I think we're going to see interesting scientific applications in the area of random quantum circuits, things like CRNRG, auto experiments having to do with information scrambling in quantum systems, which is related to quantum gravity, because we have shown that these particular problems map very naturally to our architectures, and they're very hard to simulate classically, despite a lot of improvements, actually, which has been very interesting as well on classical methods, tensor network in particular. This problem remains exponentially hard for classical algorithms, but of course, they're only polynomial for quantum computers, and we can map them naturally to quantum computers, and we can do already random quantum circuits that are very hard to simulate. Okay, so that's one area where we will see scientific applications, or we're already seeing scientific applications. Another area is spin models and the Bosser-Hubbard model. So these are more like physical problems. And the reason why I'm optimistic that we can see scientific applications in this area is, again, because we can map them to the hardware directly. And because these are quantum problems, we have an exponential speed up. So that's an area of low risk. That's what they are in blue. But arguably not the highest impact because they are more scientific problems that are interesting to the physics community. But it's unclear how much application they have in industry, although that's worth exploring, for instance, in the case of CRNG. Then we have NISQ applications that I will say are in yellow, which have higher risk. So we're cautiously optimistic that in NISQ, we're going to be able to do interesting scientific discoveries here, like fermionic simulation, and arguably that has more impact because that's related to chemistry, material science, things like that, which obviously have huge industrial applications. So I will talk about this as well. We have, the reason why we're cautiously optimistic is because we still have an exponential speed up, and it doesn't map as directly to the hardware as the spin models. You have to do some transformations, but there are still a lot of algorithmic improvements that we can do to really land this application, and I will talk about that with one example. And then the last area is classical problems, like classical machine learning or classical optimization. Not quantum machine learning, as John talked about. I'm more optimistic about that, but classical machine learning with classical data. So I will say we're not as optimistic, or I'm even pessimistic that we're going to be able to see NISQ applications, although arguably they have a lot more value. So they can be applied in, not just in chemistry and physics, but in general industry problems. And the reason is that, for most of these problems, we do not have an exponential speed up. So it's an example where we do. But even when we have an exponential speed up, it requires, as far as we can tell, for the cases where we have an exponential speed up, very complicated circuits that we're not going to be able to run without error correction. So I will also mention this at the end with actually a counterexample, meaning some advancements in quantum-inspired classical algorithms. Okay, so one example of NISC applications is information scrambling. Here you see an image of how the circuit looks like. The basic idea here is you want to understand how information scrambles, how information moves in quantum systems. So there is an ancilla qubit where we're doing our measurements, and we're going to have a butterfly operation somewhere in the circuit where we do a perturbation. And what you want to measure is how fast the perturbation affects your ancilla qubit. How does information move on quantum circuits? This is measured with what is called OTOC, out-of-time order correlations. So the circuits look like this, and the unitary here are random circuits. So this is an application of random circuits. We know that this is very hard to simulate classically. This is an experiment that we also published this year in Science. So we actually did, when we were doing this experiment, some careful comparison with the latest classical algorithms to see at what point we're going to be able to do OTOC experiments that cannot be reproduced by the best algorithms even in a supercomputer. So that's the plot that you see there. You basically have to measure the OTOC signal where the signal to noise ratio is larger than 1. So that's the plot on the bottom. The y-axis is the signal to noise ratio, it has to be bigger than 1. The x-axis is the number of I-swaps in the circuit. These are highly entangling gates, and it's basically a measure of the complexity of simulating the circuit. The more I-swaps you have, the harder it is to simulate. And what we see is that when we benchmark these circuits with tensor networks, so the latest classical algorithms, we can simulate up to around 420 I-swaps. If we were going to use a full Summit supercomputer, which we didn't, but we can extrapolate. Whereas the signal-to-noise ratio goes below 1 to around 220 I-swaps. So we're not in the regime where we cannot simulate this experiment anymore. But we were able to perform the experiment up to 220 I-swaps. We're able, or we will be able, if we try hard, to do 420 I-swaps with the Summit supercomputer. So if we lower the error rate by a factor of 2, then we go above 420, 440 I-swaps in an experiment, and we will enter a regime again for this specific application, where we are doing computations that cannot be reproduced with the best algorithms on a supercomputer. So, I'm optimistic that we're going to improve these error rates, and we're going to see applications along these lines in NISC. Here is another example. This is not as much about computation, but actually about realization of a new phase of matter, of a physical system. So this is the time crystal paper that we published recently as well in collaboration with Princeton and Stanford. And the basic idea, well, a time crystal is time periodic system, the same way that a space crystal has periodicity in space, a time crystal has periodicity in time. So in that sense, it's like a pendulum, but the difference with a pendulum is that this periodicity in time is robust. Even when you change the parameters of the system, it's always the same frequency, the Floquet frequency. So in the left, you see the circuit that we're doing. It has some phase flips, X, that will flip the spin up and down, so you will expect the periodicity there. But crucially, there is an exponent, the parameter J. So if J is 1, nothing surprising, you're just flipping back and forth, because then you just have phases after that. But when J is different than 1, if you didn't have the entangling gates, the CC gates that you see after the bit flip, then you wouldn't see the same periodicity. Without the entangling gates, you move the parameter J, the periodicity changes as you will expect, because you're not doing a complete flip in every cycle. But once you entangle the system for complicated reasons, well, it's basically a phase of matter in some sense, then even when you move the parameter J up to some threshold, you still see exactly the same periodicity. So this is robust. And this is actually as well quite robust to the choices of the parameters of your entangling gates and the choice of your single qubit gates. So anyway, it's an interesting phase of matter that has been proposed by condensed matter physicists, not by us. They came with a proposal to do this in our experiment, and some other people have done this before in less convincing demonstrations, I guess. And in the right, you actually see the experimental result. So the x-axis is the number of repetitions, the number of times we do this circuit on the left, the number of Floquet cycles. That's the x-axis. And the y-axis is the qubit And what the color tells you is if the qubit returns to the same position or not. So you start with any arbitrary position, and if it returns to the same position after 2 cycles, then you have a 1, and if it goes to exactly the opposite position, it's a -1, so blue. And you see that it actually oscillates independently of the parameters between, well, the correlation oscillates exactly between 1 and -1, even when we change the parameters. So to be able to see this nice convincing signal that, in principle, if there was no decoherence, this will continue forever, you need to be able to perform the experiment for a large number of cycles, up to 100. So it's 100 repetitions of that circuit with up to 20 qubits. It's a lot of gates. So to really see this nice signal, we have to do a lot of error mitigation techniques as well, which is very important in NISQ. Okay, so that was the green area where, I'm very optimistic that we can see scientific applications in NISQ, and arguably we're seeing some of that already. Now for the yellow area, which is fermionic simulations related to things like quantum chemistry. So here is another recent paper. It's a collaboration that we did with Yonghoo Lee. Bill will be presenting tomorrow. And it's a new quantum classical hybrid algorithm to do fermionic simulations in quantum computers. So to do fermionic simulations, as I said, we have an exponential speedups because these are quantum systems. So exponential classical time, polynomial quantum time. But it's harder than spin models or random circuits because generally you have to do these transformations to fermions. That increases the overhead. And actually to solve a realistic problem, well, there is a lot of extra computation you have to do around to map an interesting molecule to your hardware, for instance. So this hybrid algorithm is a version of quantum Monte Carlo. So in this version of quantum Monte Carlo, it's an imaginary time evolution of many walkers. And you basically are gonna get an estimate of the ground state energy of the chemical system of interest by evolving some efficient classical workers and then averaging them. Now the problem with that is that because these are fermions, when you try to get an estimate of your energy by averaging the result that you're getting over many walkers in this Monte Carlo fashion, you're going to run into a sign problem, typical for fermionic simulations. Sometimes the result that you get from your walkers is positive, sometimes it's negative, and the positive and negative results average out, so you don't get, because of the same problem, a good estimate of your energy. Now it turns out that people has been, of course, trying techniques to solve this same problem, to get better approximations, which basically have to do with getting a good ansatz for how your solution might look like. So you kill the walkers of the negative sign, let's say, and just keep the right walkers with the positive sign. Normally, when you do this, because you're killing walkers with a negative sign, you're also biasing your estimation of the energy. But if you have a good enough ansatz, well, then it turns out you're going to kill the right walkers. You can get an unbiased solution. One interesting thing about this paper, actually, as well, is that it uses shadow tomography, which is a recent result, mostly from Caltech and John Preskill and collaborations. And bottom line, without getting into the details, the measurement that you do in the quantum computer, which is basically going to allow you to estimate the overlap between your trial wave function and the walkers, you just have to do this shadow tomography once for your trial wave function, and then you're going to be able to estimate the overlap that you need for the walkers. So actually, the computation, interestingly, in this particular implementation is independent of the molecule that you're trying, which is an interesting paradigm. You can pre-compute your shadow tomography for a trial wave function, and in principle, at some point, make that public, take it in a library, and then use these algorithms with shadow tomography to improve classical quantum Monte Carlo, even without communication with the quantum computers. Quite an interesting paradigm. There's of course, improvements that we need to do. So first, the good news is if you look at the plot, well, you have on the left is the circuit of the trial wave function and how you do the shadow tomography. You store this data, then you're going to calculate these overlaps. On the right, you have two of the implementations we did for nitrogen with 2 qubits and for diamond with 16 qubits. And then the different colors are different classical methods, different polynomial classical approximation algorithms. This particular algorithm, which is AF quantum Monte Carlo, works really well for these problems. But it's very interesting that the QC quantum computing quantum Monte Carlo outperforms the mean field quantum Monte Carlo because it's using a trial wave function that you can do efficiently in a quantum computer and estimate the overlaps efficiently, which is not possible with classical algorithms. So that's I think an impressive result of this paper, that the quantum part actually speeds up the corresponding classical part and scales quite well. So we were able to do experiments with very high precision with up to 16 qubits. There are things that need to be resolved eventually. Actually, the concrete subautomorphic implementation here has exponential cost, but that depends on the flavor of QMC that was done because that's the software that we had. So there will be follow-up work to do it with subautomorphy without exponential cost. Okay, and now the last of these NISQ applications, which is when you have classical data, so classical optimization and classical machine learning. So this is actually another result that we presented recently on a classical quantum-inspired Monte Carlo optimization. So it's a non-local Monte Carlo optimization. This follows from a lot of work we've been doing benchmarking quantum algorithms, quantum annealers, things like that, against classical algorithms. So we've been working quite hard on understanding ideas related to tunneling, so non-local moves, right? So normally classical algorithms like Monte Carlo, they have local moves. You are going to flip your energy depending on your neighbors. But well, the idea of quantum annealing, for instance, is that you're going to be able to exploit quantum tunneling, so non-local optimization moves. So we've been thinking about that for a long time, and this is a paper led by Masood where, well, we present a new algorithm that implements a version of quantum-inspired non-local loops. So I won't get into the details of how this works. Feel free to ask Masood, he's around. But here is the benchmarking results. So on the left, this is for random four-sat instances close to the insatisfiability threshold. So hard four-sat instances with up to 5,000 variables and 50,000 clauses. And on the left, we are comparing with WalkSat, basically. WalkSat is a popular heuristic that is used for satisfiability problems, right? And we see that if we look at the number of violations, that's the y-axis, then our algorithms, the non-local Monte Carlo algorithms in blue, clearly outperform by more than an order of magnitudes the number of violations. So they have a lot less violations than WalkSat. And the y-axis here is we order instances by their complexity, which is a different story. The point is that we're beating WalkSat, which is a standard workhorse for this kind of problem, by more than an order of magnitude. Now, I think even more interestingly, on the right plot, we're comparing with survey propagation. Now, survey propagation is a very interesting algorithm, also it's physics inspired. It's, came out of the work of Parisi and others that were awarded the Nobel Prize, and it works particularly well for this kind of problems. So another physics inspired algorithm. And we were really happy to see that we were able to do better than survey propagation, even in this problem where survey propagation works particularly well. Now, survey propagation is a deterministic algorithm. The non-local Monte Carlo algorithm is a heuristic, so if you run it different times, you will get different answers. But in general, well, as you can get from the left, the variation is not that large, and there are many instances. In a few instances, survey propagation did better. Maybe we run more non-local Monte Carlo, we will improve our answer. But in most of the instances, we do better than survey propagation and sometimes significantly better. So the point of this slide, other than, well, here is an interesting new physics-inspired, quantum-inspired classical optimization, is that if you're trying to work on quantum algorithms for quantum optimization, for classical optimization, then you have to be very careful because there is a stiff competition with amazing classical hardware, and the classical algorithms just keep improving. Okay, so finally, I would just like to talk a little bit about simulators. So as I said, I'm very optimistic that we're going to keep seeing good NISQ scientific applications, and we're really seeing that already. But it takes a lot of work to get one of these experiments to work well. I mentioned that, for instance, on the time crystal paper, but also on the auto paper. In all our papers, it just takes, it's not you write the program, you map it to your hardware, you run it, you get the result, and you're done. You have to spend a lot of time not just learning how to compile your program better, but actually doing a lot of ad hoc error mitigation techniques. So there is this error in your results, and you have to come up with a lot of post-processing, which I'm not going to get into, but it's an involved process to come up with good polynomial error mitigation techniques that will unbias your errors, that will correct your errors so you can get the results that I was showing. So one way to do this, well, if you have access to hardware, then that's great, and actually it's a big motivation. But you can actually try to do a lot of this work with classical algorithms. So we put out recently a white paper on our workhorse classical simulation algorithm for quantum circuits. It's called QSIM. It's very well integrated with Circ, which is our open framework for writing quantum circuits. And it works really well in cloud and Colab, things like that. And it's fast. So on the plot on the left, you can see for random circuits, these are different machines in cloud. So you can do up to, let's say, 30 qubits, which is already not a small number. It's order 10 seconds if you use one of these standard 60 machines. So that's a machine with 60 cores. Not huge, but a good machine. Is maybe an order of magnitude slower if you're using a small virtual machine. So order 20, 30 seconds. And then if you use a GPU, then you can get this simulation done in order of seconds, like with an NVIDIA A100. So again, you can get a lot of use out of simulations, but I think for the most interesting use cases, you need to simulate noise. So we've been working quite hard on actually implementing noise simulations with QSIM, with our high-performance simulator in a way that works well in cloud as well. And the way we do it, well, if you want to get to beyond I don't know 18 qubits, you have to do quantum trajectories. So basically, you're going to do at every trajectory is going to be a simulation of the circuit with some particular instantiation of the noise. So you won't know how to do this. But we did some implementation improvements, which I haven't heard before. And the bottom line with this new method, which we call delayed inner product, is that for low noise, which is the standard situation that you want to simulate if you're looking into NISQ applications, low is quite noise. For low noise, the cost of doing a quantum trajectory is actually very close to the computational cost of the time. Is actually very close to the time without noise, which I think was not the case before with this new algorithm technique of delayed inner product. And we actually published in the same white paper an approximate noise model that we have benchmarked against some of our experiments that will let everybody to just grab this open source simulation, rent a machine, or just run on your workstation and try to come up with interesting new algorithms. And with this, I would like to conclude. Thank you very much.